Alright, let's talk about AlphaStar, Grandmaster-level in StarCraft II using multi-agent reinforcement learning. The corresponding paper looks like this and is by Oriol Vinyals et al. From DeepMind and has been published in the Journal of Nature recently. Now, let me say this first. Stop publishing in Nature. This is a journal, it's not open access. It makes its readers pay for getting the article. So, actually, you can access this article or a public version of it for free, but you can't print it, you can't download it unless you pay for it. And this, to me, it seems ridiculous because none of this money goes to the authors of the article. None of this money goes to the reviewers. The review quality isn't notably better, at least in the field of computer science. All of this is a publicity stunt by DeepMind because Nature has been kind of impactful in the last decades. It's like, ooh, look at me. I got a big dick. I publish in Nature. Nothing more than that. It's like OpenAI saying their model is too dangerous to release to the world. I guess DeepMind might make the same claim about AlphaStar. It's like too dangerous of a StarCraft player. Yeah, so stop this. Publish your research in open access. Nature or journals like these for computer science. It's a remnant of the last century. So come on and join everyone else in distributing knowledge. All right, rant over. Let's jump into this article. So the article describes how to train a reinforcement learning agent to play the game of StarCraft II. So StarCraft II is this game for everyone who doesn't know. Just very quickly explain the game. StarCraft II is a real-time strategy game, and you're kind of in this top third-person view, and you control your units. And the goal is kind of to move your units around and first of all build up buildings, and using those buildings you can then produce more and more diverse units, and ultimately you want to kind of produce some sort of army that can go to the opponent and destroy the opponent's base. So you control all of this on a computer using a mouse and a keyboard, and StarCraft is notable for being very balanced. So there are 3 different races you can play. So the first are the Terran, which are kind of human-ish. They have marines and tanks and helicopters, I believe, and things like this. Then the Protoss are some sort of alien race that are super advanced, so they can teleport and have energy shields and things like that. And then the last are the Zerg, and the Zerg are kind of icky ground-dwelling creatures that infect things and spread like a disease. So the interesting thing here is, compared to other real-time strategy games, is that the 3 races, they play very different. So they have the game is almost a different game if you play as a different race, but they're so well balanced that almost any matchup is kind of a fair game between equally skilled players. So that's makes StarCraft pretty unique. Also pretty unique is the very, very high action per minute rates that pro players get. Like they play this insanely fast. So a game lasts about 10 to 15 minutes, and as I said, the goal is to destroy the enemy base. All right. So to train an RL agent to play this is very hard because like the action space is very high. You have to target with your mouse part of the screen, right? You have to look what is on the screen. What can I do? Right? There's this mini map down here. There are things you could do. There are opponents you can target and so on. So all of this is very, very, very difficult for an RL agent. And at the end, right, after 10 minutes, right, you play, and after 10 minutes you either win or you lose. And the RL agent has to figure out which of the actions that I did during those 10 minutes, right, was it this one, was it this one, which led to me winning or losing. These are very hard problems for reinforcement learning. And the DeepMind has combined almost every trick in the book known so far to RL to achieve this. Now, the main contribution, I'd say, here that is novel is what is called league training, and we'll get to that. So first of all, if you don't know what reinforcement learning is basically what I just described. You have an input, right, which could be this thing here, and you have a set of actions. You have a set of actions that you can do, which the set of actions here is anywhere you can click, right? You can click anywhere on the screen, and you have to do this over and over and over and over again until you either win or you lose. And from that, you will at the end receive, you win or you lose, and then you have to kind of learn to play the game. So it's machine learning hardcore, because you get minimal information and have to achieve a lot of things from it. So the first thing that DeepMind actually does is it does supervised learning. And we'll get into how exactly the model works later. But first thing DeepMind does is it trains an agent to simply imitate humans, right? So you have human data, and from the human data, so these are games played by humans, good humans, right? Not people like me. So these are games played with humans from a significantly high elo. And the first thing you extract is this z here. Now z is called a statistics vector, and as I understand it, it's mainly the build order, which means in which order do you build your buildings and units. And this is very important in StarCraft. This is a strategic decision where you say, okay, first I'm going to build 3 worker units. This is like 3 workers, worker, and then I'm going to build a house, and then I'm going to, and so on. So these are major strategic decisions that you kind of have to make with minutes ahead of time to plan in advance. And this is kind of stays constant for the game. So this is extracted and provided to the model as an input. So what is the current strategy, basically, the current overall strategy? The second thing that is extracted is at every time step, the observation that the humans had, so the screen that the humans see, and also the actions that the human did, right? So the human takes its mouse and clicks somewhere, right? This is supposed to be a mouse pointer, and clicks here, right? And then the model, this part here, this is the model, and this is the policy function of the model. So the policy decides what to do, right? Is trained to match the action that the human did. So in essence, first you train an agent to simply imitate humans. And this you can do by supervised learning, right? This is classic machine learning. Each step you have this input, which is an image, and you have the strategy you're trying to follow. And from these two, you're simply trying to match the action that the human did, assuming the human made a good decision. So this is how you initialize, right? You don't start from scratch. Now, I have to say that even though this name is AlphaStar, it has surprisingly little to do with AlphaGo or AlphaZero that DeepMind has done before. Mainly, this is entirely model-free reinforcement learning, and goes more into the direction of classic deep RL. And you can see with the human data, you can already get pretty far. So these down here are the leagues of StarCraft, and this here are percentiles of players. And you see with the supervised training, you can get better than 80-85% of human players already, right? So pretty impressive already, simply by imitating humans. Now, so the way to further improve this, and let's actually go first into how the model looks like. So down here they describe this model. That's it. So the model is supposed to map from input to output. So from the screen that the agent sees, right, and some other things, to what the agent's going to do, to an action A. Right? If you simply do this at every time step, then you have a game-playing agent. So first, the question is, of course, how does this happen? Now, the input isn't only the thing that the agent sees, which is this, the mini-map, and the mini-map. I believe that's the mini-map, or the entire map. Well, it's in essence, it is a picture. It is also a list of entities. So the game engine extracts a list of entities, and these can be inside the screen here and outside the screen for friendly. So the assumption is the agent knows about all of its units and where they are and what their statistics are. So in this entities thing, for each entity you have a list of what is its health, what is its type, what is its position, does it carry any items, and so on. All the things you need to know about this entity. This is in this list of entities. And along with that also opponent entities, but only the ones that are on screen. Right? So all of this goes into this list of entities. And then the next features are scalar features. And as I understand it, scalar features are things like what race are you playing currently, what time is it in the game, and so on. So these are additional features. And also baseline features. And this is mainly used to train the value network. And this is not going to make sense if you know nothing about reinforcement learning, but one main contribution of this paper is, or not contribution, but kind of thing that they claim is that for computing the value network, they also use the observations, so all of this, of the opponent player. Because you know this during training, because you're doing self-play, and you don't need this value network during inference, you can actually do this, and this improves performance significantly. All right, so that's just for people who know RL very well. Everyone else, don't worry too much about these things. All right, so these are the inputs, the scalar features, the entity, and the minimap. Each one goes through separate encoders. So the minimap goes through a ResNet, which is a convolutional network, and the entities go through a transformer, which is kind of a thing to, it's appropriate to encode a set of entities, right? Scalar features go through a classic feed-forward network, MLP. All of these get combined here into a deep LSTM that goes over time. Now the deep LSTM is what really makes the strategy, because each time step, a screen like this is input into the thing. Now, but the agent also needs to remember what did it do last steps, 2 steps ago, right? This is important because you don't have full observability. You need to know what did I do in the past, and that's where so if the last step you saw this screen and the step before you saw this screen, right, then all of this would go through this encoding step into the LSTM, right? So the LSTM will encode now over time all of these different steps. And so you can kind of say, all right, if I have just started building a building, I should probably not build the same building again, even though I can't see it on the screen, right? Because I know that 3 steps ago I did start building build a building. Yeah, so this is kind of the LSTM is basically where you integrate your strategy over time. So from the LSTM, you have to make 2 predictions. You have to make a prediction of what to do. This is the action. And how valuable is your current state. And how valuable is your current state? This is called the value network usually. This is a core component of deep reinforcement learning. these two components, one is called the policy, which would be everything over here, and one is called the value network, which is called everything over here. These are the things you need to do actor-critic learning, and actor-critic learning is the current state of the art in DeepRL. So DeepMind does nothing else here, except, as I said, they use these baseline features for the value network. But if you don't know what a value network is, don't worry about it. The important part for playing the game is actually the part over here, called the policy. So first you need to decide what action you do. And there are many action types in StarCraft. As I already said, you can build a building, you can move a unit, you can actually move the camera. That's an action type, right? Because you want to maybe see what's over here or over here or over here. So that's an action you can do. And if you have decided on what action you want to do, you have to decide, when do I do it? So you see the action type, once you figured it out, it goes into the next neural network. And that decides, okay, when do I do it? When do I do this action? So it specifies a delay. Then once you've decided what to do and when to do it, it goes into the next neural network, and that decides, should I put this into the queue of actions? Because the agent here is limited to a certain number of actions per second. And I think it's 22 actions per 5 seconds or something like this. So in order to mimic, human limitations. So there's a queue of actions to be executed, and the agent needs to decide, do I really is this action so important to put it into the queue? All right, if you have decided what to do, when to do it, whether you would like to do it at all, right? Then you have to say, it goes into the next neural network, and you have to say, all right, which units do I want to do it with, right? If you want to build a building, you can have to choose one or many workers to do it. I don't actually know how StarCraft works in this. I'm a bit of a noob, but you have to select units with which to do the action for most of the thing. And there I like the use of a pointer network here. So what a pointer network is a network that can point to its own input. It's sort of like an attention network, but not really. In a pointer network, if you have a set of inputs like we have here, so entity, 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 right? All these entities, and you can see the entity embedding. The entity encoder actually has skip connections that go here, right? So this network directly gets these entities as input. It can then, right? Then you have a neural network on top of that. Neural network that the neural network takes all of these things as an input. And what the neural network will output is a pointer to one of these things, right? You can say, look, I point to this thing right here. This is called a pointer network. And yeah, as I said, it's different from an attention network, so an attention network is where you get a distribution. Actually, you get a distribution in both cases. There is a difference, but we don't have to really time to go into it here. But in essence, with a pointer network, you can select which of these entities you want to do something with. All right, now you've decided on which action, when, whether to queue it, with which unit to do it. Now you have to decide for some actions, for example, if the action is attack or heal or something like this, target unit. Which unit do you want to target? Or which location on the map you want to target. This is the target point here. And you can see again, here are skip connections from the entity encoder and from the spatial encoder to these things. And while the target unit is an attention network, it has this much like a pointer network, it will kind of point to places in lists. The target point is a deconvolutional ResNet. What that means is, so you have this spatial encoder here, will embed the minimap. So there will be a neural network right here. Actually, let's draw the neural network in this color. Right here, it will give you an embedding of that, right? And that's what you feed into. That's what you feed, for example, into the LSTM. But then what you do is you have a deconvolutional network, which again produces a minimap. But on this minimap, it's not the original minimap, but it's kind of a distribution of locations. So it said, look, here do I want to point, right? So this neural network is responsible for producing this dot on the minimap, basically saying, okay, I know what to do, when to do it, with which units to do it, and so on. I want to do it right here on the minimap. Okay, and now you have it, right? You go from the input, which are these things, the minimap, the entities, and so on, to what do I want to do, where, when, with which units, and so on, right? This is called a policy, and it's extremely complicated. Every one of these boxes here is a neural network, and you can see it's very it's a lot to train, and they have a lot of resources since they are DeepMind, but that's the main thing. All right, they have a few tricks to train this, and we won't go too much into this, but one of the tricks is vtrace from the Impala paper. Another trick is upgoing policy update, and a third trick is TD lambda learning here. And all of these are kind of improvements onto classic actor-critic reinforcement learning style like A2C or A3C. If you are interested, then you can, look into these things. So that's how they train it. And the question now is, what's the protocol for training it? We saw, okay, there is supervised learning. Cool. Then there is reinforcement learning. All right. But you can't just apply, and this is in the reinforcement learning, this is what we said. You get kind of a reward, and the reward goes into this TD lambda and vtrace and upgoing policy update to train the value function and the policy. But the special thing that this paper introduces is what's called leak training. Now, in papers like AlphaGo or AlphaZero, what had been done is called self-play. And self-play basically means you have an agent. You have an agent, right? You have this, I'm going to draw an agent. This is supposed to be an artificial intelligence, right? How do I make it artificial? Okay, it has a little hat, right? A funky hat. It's a robot. And the robot will play a copy of itself, right? And the copy, it might be slightly different. But it basically, these two play each other and thereby become better and better and better. And you can see this like over time as the purple one gets better, the blue one gets better as well, because they kind of play against each other. And when one falls behind, right, then they simply copy over from the other one. They basically copy the other one, and then they catch up again, right? They catch up, right? And they continue competing. So by competing against each other, they get better. And this is called self-play. Now, people have noticed this kind of leads to instabilities because you can get trapped in cycles like rock, paper, scissors cycles. So what they do is they will actually, as they get better, so this is the first version, right? And the second version, they are a bit better now, so they have bigger hats, right? And here, larger hats, right? And down here they are even better, so they have like ginormous hats. But they might have some weaknesses because they only play against each other, right? So this is the same players, but over time. What they will do is they will actually occasionally play old versions of the other player or of themselves, right? Occasionally, the new versions will fall back and play old versions, or not only the current versions of the agent, or old versions of themselves, right? So this is called fictitious self-play, in that you always play you not only play your current kind of opponent or your current self. I mean, it's the same anyway because you keep copying the weights. You also play the old ones. And this paper goes a step further and says, actually, we do this, but we want to prioritize the good ones. So, for example, we know that the current ones are good, right? But we know that this particular one was also pretty good so far. So we keep making these new ones play against this one more often. And this has led to kind of an improvement in these kind of self-play algorithms. And the real new part of this AlphaStar paper is the fact that they do this league training. And in the league training, this is what it looks like, but I find this graphic rather confusing. I'd rather explain it like something like this. All right, so there is your current strategy, and you have a hat, right? And you do all of the I play against myself with the smaller hat thing, right? I play against past versions of myself. Fine. But then you also you have what's called exploiters. And an exploiter is let's call it a triangle hat, because it's very evil. What it does is it specifically targets only the current good agent, right? So this agent right here is tasked with playing old versions of itself and playing the exploiter both at the same time. But the exploiter is only tasked with playing this thing. So what it can do is it can specialize in exploiting whatever weaknesses this player has. Of course, the hope is that this player will become better in response, because there's a player trying to exploit it, right? So as this player becomes better, then this player here is reinitialized and tries to find new weaknesses, right? So as this one continues to learn, so the exploiters, they are initialized. You can see this here. So these are called the main agents, and you can see they play against each other. Right, one of them, they play against each other. They play against past versions of themselves. So these are past versions of themselves. But then there are these main exploiters, and the main exploiters, they're constantly reinitialized from human data, right? You can see this here. They're reinitialized, and they only play against these main players, right? They don't have to deal with any of the past players or playing against themselves stuff. They only try to exploit the main players, and thereby the main players get better. Once they get better than an exploiter, they are reinitialized. So the exploiters are reinitialized to find new exploits of the main agents. The third component is what's called a league exploiter, and a league exploiter is the following. So the league exploiter here, and its hat is a wavy hat. And what the league exploiter does is it plays against past versions of itself and others. So it does play against the league exploiter, with smaller wavy hat. It also plays against this thing. By the way, this here also plays against past versions of this and of everything else. You can see here the past version arrows. It goes against all past players. So this represents all the past players that ever existed. And so here, but also against past versions of this main exploiter here. But the important thing is the current main exploiter doesn't play past versions of itself, right? So this also plays this, and this plays this. So and this plays this, and this also plays this. So the league exploiter, they do take part in this whole league business, like playing against past versions of all the players, but it only plays against the main exploiters, and this is a thing that I find missing here, honestly. And I don't know if I don't understand this, but I'm pretty sure I do. Like, these also play these, and that's an arrow missing in the drawing. The league exploiters play the main agents, but the main difference between the league exploiters and the main agents is the league exploiters, they don't play themselves, right? There's no playing themselves on the league exploiters. So the league exploiters, what they can do is they can find weaknesses of the entire league and kind of train by playing against the main opponents using those found weaknesses. You bet that the main agents will get better against those major weaknesses of the entire league, right? So the main agents, first of all, they get better by playing the main exploiters, because the main exploiters are mainly trying to exploit the main agents. The main agents also get better by playing the league exploiters, because the league exploiters find weaknesses of the entire league, right? So, and the main agents, they also get better by playing each other. So that makes these main agents kind of, you can say they're trained against everything under the sun, right? Against any possible exploit that can be found either in themselves or generally, and thereby they get really good at StarCraft because they can counter pretty much everything. So this is how league training works, and this is what I feel is the main contribution of this paper to the reinforcement learning world. Now, they do an ablation study here, and you can see where this ends up. So these final agents here, they end up in Grandmaster-level StarCraft and beat 99% of human players. So really, really good. They do an ablation study of all of the tricks they use. So this is pretty much all tricks they use. And you can see here, this includes these league composition, right? What happens if we only have main agents, then main exploiters, league exploiters, and you can see the elo going up. Then you can see, okay, multi-agent learning, how much does this fictitious self-play, the fact that we prioritize to strong players and so on, how much does this help? And you again see the elo going up. How much does it help that we use human data? How much does it help that we use these different networks and so on? So they have a very good kind of ablation studies of how much each of the things help. Here they investigate what if we didn't have a camera interface. So what if we could see the entire game at once and not only kind of the opponents that are within the camera? And what if we didn't need to move the camera? They investigate the off-policy learning corrections that we mentioned, and so on. So I find this very cool that they do these huge ablation studies to show really how much each of these tricks that they used helps in generating their superior performance. And here you can see how these agents develop. So over training, and they have a massive infrastructure, and they train for days. You can see this here, but you can see that the main agents just get better and better and better and better, while the main exploiters, of course, they stay the same, but they kind of keep getting reinitialized, right? So this main agent is trained to exploit this main exploiter is trained to exploit these main agents. This one is trained to exploit these one. They're not by themselves really good agents, but they're simply trained to find and exploit weaknesses of the main agents. Likewise, these League exploiters, they do get better with the League, but they are only concerned with exploiting current and past versions of the League, right? Also to make the main agents better. So everything is geared towards making these main agents better. And you can see that it actually works. They have some analysis of which builds, which units these agents build. I'm not too versed in StarCraft to comment on this, but all in all, I find this to be a very cool paper, and I find it to be described fairly clear what they do, though they do not release the source code. They release some kind of pseudocode, but the analysis and the ablations are very good. The results are, let's say, questionable because, of course, the you can't compare machines to humans, especially in a game where you have to make quick actions. Even if you limit the actions, right? They do this here, right? So they have kind of this monitoring layer which limits the actions and introduces delay and so on. But still, like if it's not the same as a human who might not always be able to do these 22 actions per 5 seconds, who if something quick happens may need to have some kind of relaxation phase and so on. But they try with these kind of delays and action limits, they try to model this these kind of limitations. So that's I find this as fair as possible. This is what I find kind of problematic. So they own units, as I said. The agent can also see the ones that are outside the camera, and that seems kind of shady, because of course you can claim humans can do whatever command groups to also control units outside the camera, but it's not really the case. So that's sort of a distinct advantage that the machine has. But yeah, in any case, I find it to be very well done, and I hope this made it a bit clearer what the exact contributions are. And with that, have a fun time playing against AlphaStar. Bye bye.